Okay, so the next part that we have here is called implication. And implication most probably comes from the basically from here. So it's basically called implication. Implication. And implication, the name most probably comes from basically in mathematical reasoning. We say, for example, P implies Q. So this basically this notation over here is read as implies. Of course, this has many different types of meanings, and I didn't really know this up to this point that I read this part. But it seems that it does have a many different ways of understanding it, and which is a little bit which is a little bit disturbing, because you wouldn't know how to think about it. But hopefully when we get into the problem, into the examples, we will know how to think about this. So but now these implications are also called if-then clauses. If-then clauses. If-then, and then there is also only if. There is also if and only if. Now, of course, these so there is this thing over here. There is this thing over here. There is this thing here, and we also have this thing. And these are not necessarily, of course, the same things. Now, talking about if-then, we can understand it this way. So let's consider this example. It says that if you're born in some country, if you are born in some country, then you are a citizen of that country. Then you are a citizen of that country. So if you are born in some country, comma, then you are a citizen of that country. So you have a if over here, and then you have a then over in the next sentence. So of course this you could say that this is a compound statement, and it corresponds to, well, you couldn't say that it's a compound statement, but you definitely could say that it corresponds to two statements. I don't want to give you wrong information or something, wrong assumptions. You can say that this statement corresponds to two statements given by two statements P and Q, for example. P being you are born in some country. You are born in some country. And Q being you are the citizen. You are the citizen of that country. So these are the two statements this statement up here corresponds to. If I call it R, for example, so R corresponds to these two statements P and Q. So then if you have P and Q, then basically if P then Q, if P then Q says that, if P then Q, this statement, this sentence over here says that in the event if P is true, then Q must be true. So this says that in the event P is true, then Q must be true. I need to pay very close attention to this, to everything that I say here, and I'll do my best not to give you wrong information or wrong assumptions, or just strictly what is supposed to be said in this case. So it says that basically, and I'm going to go a little bit slowly so that we don't make any unnecessarily any mistakes. So then if P then Q says that in the event if P is true, in the event that P is true, then Q must be true. Now, one of the most important facts about the sentence if P then Q is that it does not say anything or places any demands on Q when P is false. So I repeat this. One of the most important points or facts about if P then Q is that it does not say anything. So basically, if P then Q does not say anything, or in other words does not place any demands on Q, or in other words does not place any demands on Q, when P is false. So what that means is that, so if P then Q says that in the event that P is true, then Q must be true. Meaning that in the event that P is true, you can definitely say that Q is true. Okay? But then if P then Q, the same thing, it does not say anything, or it does not place any demand on Q when P is false. So when P is false, what this means is that when P is false, you cannot say whether Q is true, or you cannot say whether Q is false. You just don't know anything about Q. You cannot say anything about it. Okay, so that's basically how it works. So for example, if you are not born in the country, meaning that in the case of this example, it says that if you are born in some country, you are the citizen of that country. So what this means is that, and if you use it with if P then Q, then what that means is that if you're not born in some country, then you cannot say anything about Q. Then you cannot say whether you are a citizen of that country, or you cannot say that whether you are not a citizen of that country. You don't know anything about your citizenship, right? That's basically, maybe logically or based on common sense, it doesn't make any sense, but based on the definition of if P then Q, it just basically works like that. So in basically, to put it in other words, not happening of P has no effect on happening of Q. So you can say that not happening of P, if P does not happen, it doesn't have any effect on happening of Q. So I write this: not happening of P does not have any effect on happening of Q. What that means is that if P doesn't happen, you cannot say that Q is not going to happen, or you cannot say that Q is going to happen. Maybe basically the only thing that you can say is that you cannot say anything about Q, meaning that you don't really know if Q is going to happen or not. Maybe Q happens through some other incident or through some other cause, or maybe it doesn't happen at all, but you cannot say anything about it. But when P happens, then Q will definitely happen, or Q will definitely follow, basically. So now, in case I have confused you, which I hope I have not, we are going to take an example, and through this example understand the different ways that you can understand if P then Q. And that is meaning that there are several ways of understanding if P then Q. Okay, and that's basically why I said it's a little bit disturbing if there are several ways of understanding something and there is going to be confusion or ambiguity. But hopefully in the examples we will take care of that problem. So now what we will do in order to basically when it comes to such things where there is different ways of understanding them, usually the best way to understand them is through some problems, through some example, some illustration, and that's what we want to do right now. So now suppose that you have some statement which is, for example, R, as if a number is a multiple of 9, if a number is a multiple of 9, then it is a multiple of 3. Then it is a multiple of 3. Okay, so this is your P, and this part is your Q. The second part is your Q, the first part is your P, meaning if P then Q. So now let P and Q denote these statements as P. For example, as P is a number is a multiple of 9, a number is a multiple of 9, and Q, let Q be a number is a multiple of 3. Now if that is the case, then if P then Q, then if P then Q is the same as the following, Now maybe the first time you would not accept it logically, but then if you just let it sink in for a while, you will understand it. It's not very intuitive. I mean, not all of the ways of understanding if P then Q is very intuitive. So number one, so then we said that if P then Q is the same as the following. So number one, we can say that P implies Q is denoted by P implies Q. So if P then Q is actually the same thing as P implies Q. Okay, it's basically the exact same thing. P implies Q. So P implies Q, this thing over here, is denoted by P implies this notation. P implies Q. And this symbol over here, this symbol stands for implies. This symbol stands for implies. Now this says that a number is a multiple of 9. So this basically in the example that we had over here, if the statement P is a number is a multiple of 9, and Q is a number is a multiple of 3, so then P then Q, or P implies Q, says that a number is a multiple of 9 implies that it is a multiple of 3. Okay, but we will understand what this means later. So then P implies Q. This says basically that a number is a multiple of 9. A number is a multiple of 9. So this statement over here, this implies that it is a multiple of 3. That it is a multiple. That it is a multiple of 3. That's the meaning of this. Now number two is basically you could P implies Q, or if P then Q, you can understand it also as P is a sufficient condition for Q. P is a sufficient condition for Q, which means that knowing that a number as a multiple of 9 is sufficient to conclude that it is a multiple of 3. So meaning that P is a sufficient condition of Q, meaning that knowing that a number is, so if P is a sufficient condition for Q, meaning that knowing a number is multiple of 9 it's evidence enough to conclude that the number is a multiple of 3. Okay, so P is a sufficient condition for Q. And there is another way to understand this, which is basically P only if Q. P only if Q. Which means that the number is a multiple of 9 only if it is a multiple of 3. Which means that this says that basically that a number is a multiple of 9. A number is a multiple of 9. Is a multiple of 9 only if it is a multiple a multiple of 3. So here we said if P then Q, here we said if P then Q, and P is a number is a multiple of 9. Q is a number is a multiple of 3. So then if P then Q, you can also understand it in the form P only if Q, meaning that a number is a multiple of 9. A number is a multiple of 9 only if the number is a multiple of 3. And that's actually true. If a number is not a multiple of 3, it cannot be a multiple of 9. The number first has to be a multiple of 3, and then another 3, and then those two 3's are multiplied together. That gives you a 9, right? So that's another way of understanding it. P only if Q. And there is another way of understanding this, which is number 4, which is basically Q is a necessary condition for P. Q is a necessary condition for P. Now this says that when a number is multiple of 9, it is necessarily a multiple of 3, which is basically the same thing, which is kind of basically the same thing that we said in number 3. So this says that basically when a number is multiple of 9, when a number is a multiple of 9, it is necessarily a multiple of 3. It is necessarily a multiple of 3. So number 4 is Q is a necessary condition for P. Q is a necessary condition for P, meaning that when a number is a multiple of 9, it is necessarily Q is a necessary condition for P. So when a number is a multiple of 9, it is necessarily a multiple of 3. You just need to understand this in the context of this example, and then hopefully you will be able to apply it to other examples. But first you need to understand it in the context of this example well. And also number 5 means that not Q implies not P. Not Q implies not P. This is the negation of Q, and this is the negation of P. Now this means that if a number is not a multiple of 3, then it is not a multiple of 9, because Q is basically, Q, as we said here, is a number is a multiple of 3. P is a number is a multiple of 9. Now over there we said not Q implies not P, meaning that if a number is not a multiple of 3, then it's not going to be a multiple of 9. So that's basically that. Now in the next video we are going to talk about contrapositive and converse. These are also very, very helpful in, well, any sort of theorem that you want to prove. You are going to need contrapositive and converse, at least converse. And about contrapositive I cannot say anything right now, but we will do that in the next video. So I'll see you in the next video.